Okay, let's resume the lesson. Here we are. So now we will talk about an application that was developed by collaboration between Cineca and Polytechnic of Milan. And Riccardo Mergoni will present molecular unfolding with a quantum annealer. And yes, hi Riccardo, welcome back. And the floor is yours. Thanks a lot for being here also today.
So can you see the slides?
Yes, we can see it and we can hear you. Thanks.
Okay. So first, I see there are some questions in the chat regarding the current status of quantum annealing, quantum gate models. Okay, I see Daniele answered. So, well, basically, okay, now we, in the next talk, you're going to see that, okay, some application of quantum annealing in drug discovery. Okay, so as you have already said it in the chat, yeah, probably now quantum annealing, quantum annealers, since are larger in size, can handle problems that are beyond the reach of what gate model can do. So computers like IBM computer or Google quantum computer, or so gate model quantum computers. My idea is that right now, however, these devices are still prototypes. Yeah. So what you can do is something very close to basic research. There is not much, so probably quantum annealer is closer to some practical application, but still we have to understand if it can provide some advantage for specific problems. Okay. For what concern programming languages, especially gate model may seem very may look like assembler. Okay. Because you're operating on gates. Yeah. Yeah. My idea is that till now, nobody knows exactly, okay, what, So there is the quantum annealing on one side, and we don't know, but so we have to keep an eye on it, as well as on the other gate model quantum computers, even though they are limited in size. So nobody knows what will happen in the next years. So IBM says that they are going to have gate model quantum computers of size 1000 qubit by 2023, more or less 2025. So with 1000 quantum gate model quantum computer, probably you can run things that we have seen yesterday, like VQE for molecular simulation, that are beyond what we can do today with classical computers. So right now is still not clear where is going to be the advantage. Who's going to be the first to reach an advantage, if quantum annealers or or quantum gate model quantum computers. But I mean, in the last years there were some. So with the paper from Google, the quantum supremacy paper, so things started to change. Okay, so we started to so we understood that we're close. So that was the first step, first essential step to reaching a quantum advantage for real world problems. Okay. Okay. Yeah, what he's saying, what he's writing also Daniele in the chat is also, yeah, also very true. Okay. However, so the aim of this talk is to present you this work that we did with together with Polytechnic of Milan. So with Gianluca Palermo, Professor Gianluca Palermo, and his student Kevin, and with Daniele and me. So what we had a collaboration with D-Wave that gave us computational hours in on their machines, both the D-Wave 2000 and the D-Wave 500 5000 qubits, for problems that were related like to somehow to the COVID pandemic. Okay, so what we did was we used the D-Wave for optimization problem, which is the molecular unfolding problem. So we have to unfold the best way a molecule, and this is an essential step in, which is an essential step in drug discovery. And yeah, we worked with Gianluca and Kevin because Gianluca is an expert in the classical part, okay, how to realize this on classical machine and classical supercomputers for concern, so this docking part. Okay, so let me go on. Okay, so what is exactly molecular docking? So it is a method to calculate the preferred position and shape of one molecule to a second, okay, when they are bound to each other. So basically we have the target, that is a large molecule, okay, it could be the virus, I don't know, then the ligand, which is some protein or some small molecule that has to dock, so has to enter, so in some pocket, in some, so the target, so has some pocket, and this process is the molecular docking. Okay, so what you usually do, you consider both shape complementarity, so the shape of your ligand or the molecule, so they represent, for example, your the medicine, okay, the drug that you want to find that inactivate some part of the virus, for example. Okay, and you do this process on molecular docking, considering the shape complementarity, which means, yeah, the shape of the ligand must match somehow the shape of the pocket inside the target. And then there is also some scoring function related to the binding affinity. So how do they bind together? Okay. Okay, can go on. So the molecular docking process can be divided into three phases. The first one is the ligand expansion. So basically, you start from mol2. Mol2 is like the way the ligand, so the molecule that you want to analyze, is stored in a computer. So it's a file. And then what you do is analyze your file, this file on your computer, and you have some steps. So first of all, you identify which are the rotatable bonds of your molecule, of your ligand, and then you want to maximize the internal distances. You want to rotate the bonds in order to maximize the molecular volume. Then you go to the initial placement, which means you try, let's say, initial poses. You identify initial poses of the ligand, and then you start to place it into the pocket using rigid rototranslation. Okay, so start to perform the initial placement, okay, inside this pocket. Then there is the third part, that is the shape refinement, which means once you find the optimal, let's say, initial placement, you modify the rotatable bonds in order to, again, reshape the ligand and match perfectly perfectly, as much as possible, the protein pocket, okay, the pocket of your target, okay. So and so there is this at the end is docking score maximization, okay, that you do. In this work, what we did was we focused on the first part, on the ligand expansion part. So before anything starts, before the actual docking, it has been proved that finding an optimal position, an optimal shape, which means maximize, finding an optimal configuration of the rotatable bonds inside your molecule that maximizes the volume, or in other terms, maximizes the internal distances between atoms inside your molecule. So if you start from this position and then you go to initial placement, then you have your final score increases a lot. Okay, instead of starting the whole thing from an initial condition where the molecule, for example, is very folded. Okay, so the first step is actually that, to find and unfold the torsion configuration that maximizes the molecular volume, or equivalently, that maximizes the distance between fragments. Okay, so what does it mean? So this is a graph representation in 3D space of your molecule. Okay, these are the rotatable bonds. So not all the bonds between atoms are rotatable, only some of them, and we already know by default which are the rotatable bonds of some molecule. They are specified in the file that we have, that describe in the mol2 file that describes the molecule. So as you can see here, each bond split the molecule into two fragments, okay, the left one and the right one, okay. So, and this is true for every bond that is rotatable, okay. So basically, you can, if your molecule has only one rotatable, you can treat it as a two-body system where there is this rigid fragment on the right and the rigid one on the left. Okay, it's just they're considered X as a single thing. Okay, a single rigid body. Okay, so of course, okay, this rotatable ball can rotate by some angle theta high, and since in your molecule you could have, in general, a number of rotatable bonds that goes from 1 to m, then your torsion, let's say, configuration, your full torsion configuration or rotatable configuration that identifies your molecule can be expressed as a vector, okay, of this kind. So it's a vector defining the value of each rotatable bond. Okay, so as you can imagine, each torsion, so each rotatable bond is associated with a rotation matrix, okay? So for example, as you can see here, so this is schematic representation of part or a small molecule. So if the initial position of atom at the end here is A0, when I rotate this bond here, the final position will be A, that depends on theta. And you obtain the final position multiplying the initial position by this matrix. This the rotation matrix R. Okay, the rotation matrix will depend on the cosine, the sine, but also on the sine square and cosine square. Oh, no, probably okay, but for sure from the cosine, sine and the cosine. Okay, yeah, probably only so sine and cosine. Okay, of the angle. Okay. When you have multiple rotations, so I mean, for example, here, when you have multiple bonds, so if also this one is another bond, then the position after rotating theta 1 and theta 2 of atom, which is this atom that is initially in position A0, is going to be defined by the matrix product of R associated to theta 2 with the rotation matrix associated to theta 1. Okay, this is classical way of doing these things. Okay, so something about our data set. Okay, we started from the data set that we had was made in this way. So if you look at this first plot, this first histogram, it says that, so basically our data set is made up of 117 different molecules. So the number of atoms in each molecules is shown here. So the majority of the molecules had between 40 and 50 atoms. So they're picked around this interval. So some of them 30, 40, 50, 60. Then we didn't have much molecules that were too large, okay, beyond 80 atoms, okay. If you look at the fragment, so basically, as I told you, each time there is a rotatable bond, you have to split into 2 fragments, and the majority of these atoms had a number of fragments going from 10 to 20. So since usually the number of fragments are 2 times the number of rotatable bonds, this means that basically we had this is picked around 5, 10 rotatable bonds. Okay. Then, okay, if you look at the plot on the right, okay, you can see so these are the ligands, so the molecule that we analyzed, so of which we calculated the optimal unfolding. And yeah, there is a number of fragments that increased, so they are sorted in basically increasing number of fragments. And this is how the number of atoms varies with increasing fragment, basically. Okay. Okay, so some useful concept when we before we go more on the detail with the quantum annealing part. So one thing that we use, so we had to do some pre-processing on the molecules. So this one on the right is a schematic graph representation of the molecule, of this molecule shown here. And basically you consider something that is called the rotatable between centrality. So every time you consider so before you want to do anything, you want to try to understand which is the atom that is most central. So for example, in this case, so this is the definition of the degree centrality. However, this means that if you look at the atoms, the atoms that define the rotatable bonds, which are those, then I mean, when you define the rotations, and since 5 is the atom with highest centrality, all rotation will depend on basically this bond here, okay, the bond which connects 5 with 4, okay, and this is basically the idea between S centrality. So, and this is maybe more evident here, okay. So here we have all the different rotatable bonds for this molecule, okay. So for example, let's consider these 3 atoms here. If what I want to do is to consider the distance between 16 and this other distance between 16 and 12, atom 12, okay, or from another atom inside this ensemble, I have to consider, since we've seen before that positions depend on the multiplication of the rotation associated with each torsion, with each rotatable bonds. This means that if I want to calculate the distance between 16 and 12, it's going to depend on all the different rotatable bonds that you have. Okay. Here, moreover, what you can see here is that every so we highlighted the different ensembles of the different fragments. Okay, so each rotatable bonds defined a different, let's say, ensemble of atoms. Okay. Moreover, yeah, exactly. So then here, so the shortest path, because okay, when you, as I told you, yeah, when you calculate the distance between, for example, 16 and 12, you consider all the rotatable bonds between that are included in the shortest path between 16 and 12. Okay, you don't go. So, for example, if you want instead to calculate the distance between 19 and 13, you don't go along a path that include 3, for example. Okay, you go straight to this part. Okay, starting from 19. Okay, so you have to consider first the shortest part, and then only the rotatable bonds that are inside the shortest path. Okay, moreover, another preprocessing trick that you can do is the following. So basically, you can eliminate, to simplify the molecule, you can eliminate the hydrogens that are always the most external, so the endpoints, so the most external atoms. So and so optimizing them doesn't vary too much the global volume. So you can basically eliminate them, and also you can yeah, you also have to keep in mind that double, so as I told you, not all bonds are rotatable. Especially, you can also see that double and amide bonds are not rotable, so you can delete them from the list of possible torsions. Okay. Okay, let me see. Between 16, okay, between 16 and 13, they do not present the presence of rotatable bonds on a specific information on the bond. So, okay, if you want to calculate the distance between 16 and 13, I guess so. So you have to consider the shortest path, okay, between them. So it's the shortest path is probably this one. So it's 1, 2, 4, 5, 10, 11, 13. Okay, so the distance between them, so if you fix the position of 13, then you have to vary the position of 16, which may depend on, as we've seen before here, may depend on all the rotation. Now, the distance not in the graph sense, but in space, okay, in 3D space, because when you rotate this one, for example, imagine that you rotate, this rotable, then all these three will rotate in space, and so just only considering this rotable here, you modify the difference between 16 and 13. Okay, then the more, of course, the more rotatable bonds you have in the shortest path, the more they can. I mean, the rotation is complex. Okay. Yeah. Okay. So it's okay. Yeah. No, it's actually in 3D. Okay. At the end, you want so it's each atom. So this is a graphical. So you visualize the molecule as a graph, but at the end, you are interested in the positioning space of the atoms. Okay. So again, the idea is to try to unfold, which means find the configuration to maximize the molecular volume by rotating single fragments. And you can do, classically, you can do it in different ways. You can do via random search. So basically, if you imagine this is the landscape that you obtain varying theta 1 and theta 2, these two rotatable bonds. So this is a representation of a molecule. Okay. Then you can randomly pick configuration in the space, in the space of configuration, in this case of theta 1, theta 2, but general, if you have more rotatable bonds in, it's going to be a larger configuration space, and see what are the values, okay? And basically take the best one, okay? To be the best one that you find is the best configuration that you were able to find. So it's like a random process, okay? Random search. And actually these work quite well. The second part, another approach, is like a greedy approach, where it's also called geodoc, because it comes from a software, an high-performance software that we already had implemented in the past and running on our machine, which works in this way. So basically, splits the problem into single torsion problem. So you basically, in a problem like this, where you have 4 torsions, you consider only the first one at first as a rotable, while all the others are fixed. Okay, and you optimize the volume only varying theta 1. Then once you have done that, you fix the optimal theta 1 that you find, and you skip to theta 2, and you optimize by only varying theta 2. So it is an iterative process. Okay, so and usually when you arrive to theta 4, you usually have to start again. Okay, and so it's a greedy approach, and it's very fast, because every time you are only looking at single rotable bonds. Okay, so it's very fast. That's why implementing this technique on a supercomputer gives you a solution very, immediately. But the other thing is that probably it's also not the, so at the end, when you look at the volume at the score, so it's not so you get basically a fast solution, but a solution that is not so good, okay? Because of course, what you're doing is optimizing instead of 4 torsions together, you optimize 1 and then go to the next one. So it's a greedy approach. The other thing that you can do is a batch approach, where you basically you don't consider only one of them, but ensembles of them. For example, the first 2 here in order of degree centrality. Yeah. Or so you first optimize considering only the first 2, and then the second 2, or the first 3, and then the fourth one. Okay. In the most accurate case, you consider all of the molecules. I mean, all of the rotatable bonds at the same time, but then this becomes much more computationally expensive because, of course, here you are searching in a space that is much higher. Okay. Okay then. Let's go. And okay, another thing that is important to understand is that here, every time this is not random. So every time I select my number of bonds or rotatable bonds, for example, if you consider θ1, that you do a full search. Okay, it's an exhaustive search. Okay, of the possible configuration. Okay, until you find the best one. Okay, so that's why when you already are at 4 configurations, it's already starts to be quite demanding. Okay. Are there questions so far before we go into the quantum part, or the QUBO formulation and then the experiment? If so, please write in the chat. Or is it more or less clear the problem? Okay. Okay, let me go on. So we understood that what we want to find is the optimal, identify the conformation of a molecule with m torsions. So torsion, I mean rotatable bonds is the same thing. So we want to find the optimal configuration, okay, that maximizes the distances between fragments, okay, because maximizes the volume is also equivalent to maximizes the internal distances between fragments, okay. So this is the distance, okay, that we want to optimize is the sum of all the distances between fragment A and fragment B, okay, and we put it to the square because we want to avoid to have a square root, okay. So the distance is what do you mean? Not all rotation angles are permitted? You mean like you may end up in yeah, okay, yeah. This is just a, let's say, something that we didn't implement inside the QUBO. For example, you're saying when 2 atoms get like overlap, okay, you may have something like that, okay. So usually what we did is do not include that into the optimization, but leave this as a post-processing step, okay. So in optimization, you may have, it's very unlikely, I guess, because you're exactly trying to optimize all the distances, to maximize all the distances, but may have a case where the 2 are too close, but then yeah, you have the filter, a processing filter that filter out if this is not physically acceptable. Okay. Is this the question? No, okay, here it's just a geometric approach. So we don't look at the energy, just the geometry. Because as I told you, then this is the first this is the first part, okay? Then the part about the energy comes later on in the docking process, okay? This part is fair to consider this in this way, okay? Yeah, okay, so this is the geometric part. Then everything that is maybe not non-physical, it's later on in the docking process. So that's why we were able, okay, to say, okay, this is just a geometrical optimal. Then try to so everything else that is more physical comes later. Okay. Then okay, so this is the so we have to so to define our binary optimization problem, so the molecular unfolding problem is a binary optimization problem. So basically, we consider what we did was to consider discretization of the torsion angles into d possible values. So, for example, if d is equal to 2, you can have 0 or pi, for example. Okay. And we introduce a binary variable xik, which is 1 if torsion angle theta I assume value k, so theta ik, okay, and 0 otherwise. Okay, the constraint should be this one, of course, because among the possible values that an angle can have, only one should be active, so it should be active at a given time. So that's why, so we don't want, again, angles to have multiple values, because this is no meaning, okay? So that's why we put the sum over xik equal to 1. And this is something that we already seen in the past lectures, okay, about the D-wave and formalization of Kubo problems. So discretizing torsion angles in this way also enable us to discretize the sine and cosine, okay? And you can show that you can always discretize. So if you discretize the input, you can always discretize some function of this input in this way. So it is the sum of xik, which again tells you if angle theta I has value theta ik, okay? So if this is the angle, then you have to sum, okay? It's a sum, okay? And since we have also here, we should have a penalty term, so not penalty, constraint, but the constraint is the same that we have here. So with just one constraint, we can we are okay if we have sine terms or cosine terms, okay? And moreover, it's also I have also to say that since okay, sine and cosine, as I told you, appear in the rotation, but what we are doing at the end is calculating this one, which is the square of the rotation, basically. This means that we will also have sin squared, but then the sin squared, you can write it in the same way. You can always write it as a sum of the sin square x, and same thing for the cosine square, okay? So again, now the rotation becomes a function of, so it depends now on the binary variables that I introduced. Okay, so general form of the cubo, I'm going to explain in a minute why we didn't call it cube, but hubo. And so this is the general form of the cube. So this part is the constraint that you've seen before, and this is the optimization part. So we put the minus because we want to minimize, no, sorry, to we want to maximize this term. So since the d-wave finds the minimum, okay, what we wanted is to maximize this term. Okay, so that's why we put the minus. Okay. Okay then. So where d, the distance is defined in this way. So in general, since here the distance between two fragments A and B may depend on m torsions in general, at most, say, this term DAB inside the second term here may contain up to terms up to the mth order. So terms like x1, x2, x1 times x2 times x3 times x4. So m of the m order. So that's why it's not a cube. So you don't have only quadratic terms at most. The m order is in general, so the highest order in a cubo is 2 to the m. So 2 because here we have the square. M is the total number of rotatable bonds, okay, that you have. So it's probably it was a question also of some days ago. So you can formulate this problem into a binary problem, but the thing is that you can do it using terms that are higher order terms, okay? But there is always the trick that tells you if you have high order terms, you can split them into terms that are linear and quadratic. So at the end, you can always go from a cubo formulation to a cubo formulation, okay? By splitting higher order terms into sum of linear and quadratic terms. That is always possible to do. At the cost of increasing the number of variables. So you have to introduce ancillary variables. Okay. So in our problem, we basically selected a given d. D is what is d? D is the discretization on the angle. And we discretize it in this way. Okay, you have 2 pi over this delta, the precision that you want. So in general, given a molecule with m torsion is going to be the number of binary variables in the cubo is going to be d times m. Okay. So the molecules that we consider were ranging from 20 to 50 atoms. So we have the original data set that are shown you before, and we selected some of them, a bunch of molecules ranging from 20 to 50 atoms, containing 20 up to 50 atoms, and with at most 10 torsions. Okay, no, I mean all of them had 10 torsion. Okay, 10 rotatable bonds. Okay. So what we did is in our precision, in our the number of variables that we introduced was that associated with a discretization of the angle of pi over 4. Okay, so which means 45 degrees. Okay, so one may think, okay, 45 degree is a large angle. Okay, so maybe you're not properly optimizing. Okay, if 45 angle is so you should have done this with a discretization of 1 degree. Okay, but actually something that we know from previous results on our dataset is the following. So the one shown here. So it means that the degradation effect that you get going from 45 degrees versus 1 is not actually so high. Okay. Okay, so as you can see here, going from 45 to 1, you only get a degradation of 2%. Okay, if you stay like us in the limit where I mean, assuming to stay in the limit where molecules are not so, not the largest of our dataset, okay? So as you can see here, there is the degradation, which means how the volume, how much the volume becomes less precise, okay, or less degradates, okay, going from a granularity, a precision of 1 degree versus 45 or versus all these other degrees, okay. So as you can see here, so we selected 45 because we knew that the degradation is not so high, also for 45 and for molecules that we considered were basically in this range, so probably even below the 1%. So 45 degree is actually a good may seem and high that you're not doing something that is very precise, but actually it's not so important to be so precise because the degradation is still low. Okay, then now let's see what we did. So how the HUBO, the high order binary optimization problem looks like. Okay, so the number of variables, as you know, in this HUBO, so in the formulation that you have seen before, grow like d times m. So increasing the number of torsions for, so if we consider only 2 torsions, we have 16. We have to solve a problem with 16 variables, and we go to 8 torsions where we have to solve a problem with 64 variables. Okay. This is the same thing, but for the number of high order terms. Okay. So you go when the problem has only 2 rotatable bonds, so 2 torsions. There are 16 linear terms, which means 16 variables, but 182 high order terms. So terms like x1, x2, x3, or x1, x2. So okay, each one with a given coefficient in front. Okay. When we go to 4, they increase a lot and they reach 11,000. And then when you go to 5, it's more than 200,000. Okay, so that's why. So and as you may understand, so since the problem is quite hard, it's also explodes very rapidly. Okay, so increases the dimension very rapidly. So the idea that we have is to apply some approximation on the HUBO. So let's say in order to solve this like real world problem, we need to approximate the HUBO because it's too large to handle. So basically we use this function that we call the chop, which means we deleted all the terms in this HUBO. So in this polynomial, it's very huge polynomial, and we deleted all terms that were very small, like of the order of increasing order. Okay, so here basically we deleted all the terms that were whose coefficient were below 30, and here I think it's all the terms that whose coefficient was below 60. Okay, and so this means that we were able to solve up to problem with say it's up to 8 torsions, which involve basically 30,000 high order terms. Okay, so and that's what we did. Okay, we applied this. So we deleted all the terms below some threshold, and this helped us in 2 ways. So both because in this way we obtain a speed up in the construction of the polynomial that represent the HUBO, and then secondly because it's harder, it's easier in this way to transform a HUBO into a QUBO problem, no? And then thirdly because with this approximating HUBO we were able to solve this approximated problem on the D-wave alone. Okay, otherwise the problem was too large, but was so large. Okay, so okay, the idea is quite simple. Okay, you approximate and you delete all the terms that are too small compared with the others. Okay, So, okay, so are there questions so far regarding this part? If so, please write in the chat. And so, or if not, okay. In the meantime, I will continue. Okay, then. So there are. This is how the linear terms, the quadratic terms, changed with the cubo. In the cubo. So here we apply a number of torsions. So basically, you more or less see that the number of linear terms, which means of variables that you need, and quadratic terms increasing the number of torsion, fixing the same value threshold for the cut, for this chop inside the cubo polynomial. Okay, and of course fixing number of torsion, usually it decreases. Okay. Then okay, so you see that here we have up to 200 logical variables in the cubo and up to more than 2000 quadratic terms, okay, in the cube. Okay, here so the idea is now to let's try to embed the problem into the D-Wave machine and try and see what the D-Wave can do for this optimization problem. So this is the embedding. So as you can see here, we go from, for example, like in this case, from a number of linear terms, so a number of variables in logical variable in the cubo to basically 82. And the difference in brown versus red is the difference that you have going from the D-Wave advantage, so the new device with 5000 qubit, versus the D-Wave 2000, which has 2000 qubit. Okay. As you can see here, the D-Wave advantage, since it has much more qubits, but they are also much more connected, so they increase also the number of connection between them. You can basically encode the same problem using much less qubits and much less connections. Okay, and you are as close as possible to the real logical problem. Okay, so for example, let's look at this. We go from 23 logical variables that we have in the cubo to 177 in the 2000Q and 82 in the advantage. So basically, you always have, going from the new device, you have a 51% improvement. So you decrease the number of physical qubit that you need by 51%, both for concern the number of physical qubit and the length of the chains. Chains means chains of physical qubits that represent a single logical qubit. Okay. And usually what happens is that the longest the chain of physical qubit that represent a single one, the most likely you are to get an error on the chain. So the programmer will get more, you will introduce more error if you need very long chains. Okay. So here you see some results. Okay, this is the volume found in time. Okay, and for the here is just computational time, so it's not included the time that you need to construct the Hubo problem. Okay, that may require some time. Okay, especially for larger molecules. Okay, but that is something that could be also implemented in a parallel way using matrix multiplication that goes in parallel. So that could be, we think, you can speed up that part quite easily. So this is just the computational part. Okay, once the Hubo is ready and you give it to the solver, to different solvers. Okay, and these are the time that it takes for the solvers. Okay. So we have a random that we have seen at the beginning, geodoc, so the greedy approach, random is the random approach, the wave advantage, and the wave 2000, okay? And SA is simulated annealing, okay? And here is the result for 4 torsions. So among our molecules, we selected only the 4 torsions that were more internal in terms of degree centrality. So basically, you see that simulated annealing is very rapid and is able to get a good solution pretty fast. Then actually for 4 torsions, so for medium, small problems, the advantage was start a little bit slower, but then actually after 25 seconds is the one that reaches the best solution, okay? So this was a very good promising result, and it definitely outperforms the previous generation of 2000Q annealing device. Still, however, it's not as fast as simulated annealing. Then the problem starts to change when you go to higher problems. So with problem involving, higher dimensional problems, where you involve, which involve a larger number of torsions. So as you can see, already with 6 torsions, okay, advantage in 2000Q start to be much less powerful than simulated annealing and random search. And when we go to 8 torsions, okay, we have definitely lose the initial improvement that we have with the D-Wave devices. Also, you have to think that this device needs some time to sample. Okay, they need some programming time. So usually you run the D-Wave, each annealing cycle, you run it for 1 microsecond, and you run it 100 times. So, sorry, it's 10,000 times, right? So 10,000 times, each one of the 10,000 lasts 1 microsecond, okay? In theory, but then you have other time, that, like programming time, so annealing time. So this annealing time is actually 1 microsecond, but then you have readout time, delay time. So it's not like you don't just have 10,000 microseconds if you launch 10,000 anneals, okay? So you have something that is much higher. So that's why increasing the problem means you need to get to, you don't need, you need to increase also the number of samples that you do. So you probably have to go to, with 10,000 is not enough, you have to go to 1 million. Okay, so that's why start to so also the total programming time starts to be important in this case. Okay. However, so something that we discovered and could be used in the future is that simulated annealing actually is not bad. Okay, it finds a pretty good solution in a time that is very very rapidly. Okay, so it's one thing. So, however, in general, looking at again volume gain in time, so where time is expressed in seconds, is not very fair because, as you know, these devices are prototype. So what people usually do is time to solution, that is this other metric, which tells you is the total execution time over the time over the occurrences of the best solution. Okay, so usually people look at this score that is similar to something like this. Okay, something like this this ratio. Okay, and as you can see here, okay, of course you cannot compare this with the other two, but you can compare with the simulated annealing, which is the same approach basically, and you can see that increasing the problem size. Okay, simulated annealing is the lowest one, which means that is the best one. So here low is better, which means that let's say in the same time can find the best solution more times than the other. Okay, this is the meaning of the first plot. Then you have the volume gain. So here instead the higher the better. So for what concerns the volume, instead, as you can see here, as we've seen also previous slide, advantage seem to work well for small case, for small problems, but then there is this exchange. Okay, so the simulated annealing outperforms, okay, the advantage in when you go to higher order, high dimensional problems. Okay. Then what else? Okay, so okay, one metric that we so we talked about another possible metric that could be useful. It could be maybe a sign of some of what could be the advantage of the wave devices. So we came up with this metric that is the normalized volume gain per time to solution. So basically tells you, takes into account both the quality of the solution and the time to solution. So not only these two taken separately, but takes into account for both of them. And basically it's something like a measure of how fast the method fails to provide a good solution. Okay. So everything is normalized. So it's not an absolute. That's why simulated annealing in this case is lower. So this means that basically advantage, okay, seems to so as the average slope, okay, is lower for advantage. It seems like promising to say, okay, probably advantage is on the right path to beat, okay, in the future simulated annealing also for this kind of problem. Okay, because here, yeah, the higher the better. Also, yeah, I think yeah, that's it more or less. Briefly, again, the conclusion. So we tackled this problem molecular unfolding for which is an important step in molecular docking. We provided this formulation of the problem, and we also applied this approximation, what we call the CHOP, okay, increasing problem size in order to simplify the problem and fit the D-Wave processor. For what concerns the embedding on the D-Wave, so the advantage, so the 5,000 qubit one as so beats the previous generation of devices with 2,000 qubit, so it outperforms the previous one. For what concerns this absolute time solution, actually we would score the simulated annealing is the fastest one and the one which always provides a close to optimal solution. And then for what concerns this metric, which is the normalized volume gain over time to solution, yeah, we have seen something that could be promising, okay, also for quantum annealing, as seems to slow down less fast, okay, so slow down better than simulated annealing, okay, on sorry. Okay, so I think, yeah, that's it for this part.
Thank you. You talk too much. I think that you need some water because you made so many interventions here that.
Okay, again, if you have, as always, if you have asked a question, please ask.
Thanks a lot. So, is there any question? Okay, let's do it. Make this question.
Well, yes, basically yes, something like that, yeah. Yeah. Of course, yeah. If you look at the time to solution and the volume gain, yeah, the simulated annealing is always outperforming the other. Okay, let's say. So we scale them in order like for them to be on the same. Yeah, we normalize everything and then.
Okay. I don't know if it's me, but is Riccardo freezed? Or it's me that is freezed? Can you hear me? It's Riccardo. Okay. Luckily, it's happening at the end of the school. So this is the danger of an online school. Okay, so we will wait. You don't see how everything was scaled. Let's wait. Riccardo that will come back in a moment, I'm sure. Okay, here it is. No, not still.
Sorry, I had an internet connection problem.
Don't worry, Riccardo.
So yeah, I was saying, yeah, it's yeah. I think you heard my answer.
No, we didn't heard the entire answer, I think, because there is
Okay.
some other
Okay,
doubt.
so yeah, but basically the idea is what I was saying was, yeah, we normalized both the volume gain and the time to solution, and we took the ratio, okay, something like that, in order to put everything on the same scale. Are there other questions?
You cannot speak because you're muted. In what sense? Who muted you? You cannot unmute yourself? Yes, here you have an icon with apparently the organizer. Ah, I don't know. I didn't do it. I don't know who did, but now I think that you can speak. You can unmute yourself.
Gianluca, sorry, just to finish this, I think I wasn't clear in my question. You basically work out a quotient ratio between volume gain and TTS. Okay, that's straightforward, no problem. But you say it's normalization. The two, volume gain and TTS, have different units, but and you say, okay, I scale all the curves so they can be compared. But what you do is just work out a ratio. It's not really normalization, is it? Or am I wrong? Or is it the term that you use?
Okay, so we what I think is that we normalized time to solution and volume gain. So
independently from one another?
Yes, I think yes. And then we took the ratio, something like that. So that's why we call it normalized.
Okay.
So yeah.
Okay. So if there is no
probably
sorry,
no, there are no, I don't know. Probably there are other questions. I'm looking at the chat right now. I need to understand better. I don't understand very well what type of results we obtain after implementing the program into the debug. I mean, I don't understand when the variable xik is 1 or 0. Okay. Let me tell you more. So basically, our variable xik tell us define the discretization on the angle. Okay, so at the end we find if we find xik equal to 1, we know that the angle, the torsion angle theta I has some value k. Okay, so at the end it's gonna be, so it's gonna tell us which is the configuration that optimizes the distance. Okay, let me share again because I lost the sharing probably.
Yes.
1 second. Okay, I guess you can see now. So I'm not sure I can hear you.
Yes, we can hear you.
Oh, no, I wasn't sure if I was able to hear you. Okay, however, yeah, okay, let me go to the definition. Yeah, here, okay. Basically, when you find xik to be 1 at the end, you know that, for example, the angle theta 1 is gonna be theta ik, which means theta ik is a list of possible angles. So for example, 0, pi over 4, pi over 2, and so on. So if, for example, xi 1 is 1, we know that angle theta I is gonna be 0 or pi over 2. So depending on this list, okay. And the way the annealer should choose this configuration is because this configuration is the one that optimizes this part here, which is the sum of distances. Okay, so I don't know if yeah, if this explains a little bit better the question. So if this answered the question. Okay, perfect.
Okay. Is there any other question? Here in chat, we have something. No, I don't think these are the same as before. Okay, perfect. So now, before leaving you, I want only to tell you something about our computational resources. Okay, can you see my screen? I hope yes. Ricardo, do you see my screen? No, you cannot see my screen? Ah, why? Why is that? Let's retry. And now? No, really. It's really strange. Why is that? I don't know. Let's retry again.
No.
So you're continuing not seeing my screen?
No.
No.
Let me try with my screen. Can you see it?
Now.
Can you see my slides?
I can see your slides.
So, okay, maybe it was because I didn't stop. So let me try to stop correctly.
Stop the...
Yeah, stopped it. Try. You can try now.
It's completely stopped. Let's retry. Say yes, please.
No.
No. Oh my God.
Are you using 2 monitors or?
Yes, but I'm. It's the same thing that I did yesterday, so I don't know why this time is not working.
Just get out for 10 seconds and come back in the virtual room, and maybe the
maybe I can do it. Yes.
Just 5 seconds.
Yes. So I will rejoin you in 10 seconds.
Ricardo, are you there?
Yeah.
Just one question. Did you guys implement this in your group, the molecule conformation?
Yeah, exactly. Yeah, exactly. It was joint work with Politecnico Milano. Okay, Daniele, now we see, and yeah.
Oh,
yeah.
Okay.
Yeah, we did it with Kevin. That was a student at Politecnico Milano, and that was his master thesis, basically.
Did you actually touch upon the subject of chirality? I mean, change of hands of molecules that can be left-handed or right-handed, and they can coexist because they have generally the same or almost the same conformation energy. So they can, in reality, coexist. And when you make drugs or pharmaceutical, you're always concerned about whether you have 80% of chirality A and the rest of chirality B. And did you get into that, or
No,
is it too complicated?